So the working of the lift-based turbine device, lift is produced perpendicular to the flow direction, and drag is produced parallel to the flow direction. So you can see that when the wind approaches the turbine, the top of the resultant vertical axis turbine blade rotates. Since both the wind and the blade are in motion, we get a resulting relative velocity of the wind striking the blade, which is twice at an angle alpha, and this alpha is called the angle of attack. In the direction parallel to the relative wind speed, we will get a drag force that will try to push the blade in the backward direction, and perpendicular to the drag force, we will get lift force. Now, the components of the lift force and drag force will give us the necessary centripetal force that we need to rotate our turbine. Okay, so that's how our lift-based terrace turbines work, wind parameters. Now let's mention some of the wind parameters. Wind power basically measures the total kinetic energy possessed by the wind. It can be given by frac 1-2, rho AV3, where O is air density, A is the swept area, and V is the velocity of the wind. You can see that the power produced by the wind is directly proportional to the cube of the wind velocity. So the more the wind velocity, the more the power will increase. Okay, so now according to the power coefficient. What is the power coefficient? It is basically the ratio of power generated by the wind turbine to the wind power. It can be thought of as an input, what wind power is coming in, and what output you are getting from the wind turbine, the power generated. So it compares those. Tip speed ratio. A tip speed ratio basically tells us how fast our turbines are rotating with respect to the wind speed. We divide the blade tip speed by the wind speed, divided by V. Here, omega is the angular speed of the turbine, r is the radius of the turbine, and V is the wind speed. Power coefficient. Now, coming to the power coefficient curves of various models, you can see that the variable pitch vertical axis turbine, which requires a small tip speed ratio, performs better than all other turbines. This is very interesting to notice. However, the fixed pitch vertical axis turbine is not performing that well, and the horizontal axis turbine is always pretty dominant. The Savonius wind turbine performs very poorly because it is a drag-based turbine and is not that efficient, resulting in a very small CP. This is interesting to note, how the variable pitch vertical axis turbine performs better than the horizontal axis turbine at lower tip speed ratios. Because of this, variable pitch vertical axis turbines are self-starting as well, meaning they can start at very low speeds without an external power source. Pitch angle. Now let's talk about how we can vary the pitch, because we have seen that variable pitch turbines have a better CP value compared to other turbines. First, let's define the pitch angle. The pitch angle is the angle between the blade and the circular path of the blade. A simplified blade pitch changing mechanism is desired. A complex design is not recommended because it would complicate things and we wouldn't be able to achieve our objective. A 4-bar link mechanism, specifically a double crank pitching mechanism, is desired. This type of mechanism is often taught in kinematics of machinery in the mechanical engineering department. When the turbine rotates, the blade pitch changes automatically in a cyclic fashion as the turbine rotates. Here, the offset link is fixed in the wind direction. You can see how the pitch angle varies. The blade has a 0-degree angle with the circular path of the blade here, 90 degrees here, 180 degrees here, and 270 degrees here. The pitch angle is always changing. This 4-bar mechanism will be explained in the next slide. Double crank mechanism. When we fix the smallest link, we get a double crank mechanism. This is the smallest link, which is also the offset link. When we fix this, it remains fixed in the wind direction. This can be done by a wind vane. So this is the input link, this is the output link, and this is the blade. You can see the 4 bars I was talking about. When the wind strikes this blade, it rotates the input link, and this link rotates a full revolution. However, since this link is fixed, the output link also rotates a full rotation, and since we have 2 full rotations, we get 2 cranks. That's why this mechanism is called a double crank mechanism. The blade simply flaps or oscillates, but it does not make a complete revolution. That's why it is called a floating link. So, here, all the 4 links are connected by pin joints or revolute joints. The pitch angle varies sinusoidally, which can be derived by mathematical equations, though I won't go that deep into it. The blade pitch amplitude depends on the length of the offset link. This is a very important result. However, again, it involves mathematics. But what's crucial to note is that the blade pitch amplitude depends on the length of the offset link. If you increase the offset link length, the blade pitch amplitude will also increase. And if you decrease the offset link length, the blade pitch amplitude also decreases.